This video will go over the trends we see in atomic radii. That's basically the size of atoms, right? The radius, since that an atom is a sphere, the radius is, half of the diameter of that sphere. So this is the trends we see on the periodic table in the size of atoms. So we need to start this discussion with some background on ideas called electron shielding and effective nuclear charge. So let's start with magnesium atom. I know this is magnesium because it's a plus 12. That's just the number of protons in the nucleus. Okay, so this is atomic number 12. It has 12 protons. And this is a magnesium atom, so if you count the number of red dots there, those are the electrons. I see 2 in the outer shell, and then 1, 2, 3, 4, 5, 6, 7, 8 in that middle shell, and 2 in the inner shell, and so that should be 12 electrons as well. So this is a neutral magnesium atom. These outer electrons are called valence electrons, and we care most about those usually because those are the ones that are involved in chemical reactions, right? So these are the 2 electrons that magnesium atom would lose to form magnesium plus 2 ion. And that outer shell, those are also the electrons that would be involved, that would be shared in a covalent bond, and those are also the electrons that would, where some nonmetals might gain electrons in the outer shell. So the valence electrons are the ones we usually care about the most. The ones inside are called inner core electrons, and so magnesium has 10 inner core electrons and 2 valence electrons. Now, if we sort of zoom in on this area and we look at the nucleus and those electrons on that right-hand side, the electrons are going to be attracted to the nucleus, right, because positive and negative charges attract. However, these other electrons are going to repel this valence electron, and so electrons are attracted by the nucleus, but they're repelled by the other electrons. And so there's sort of a combination of effects going on. So valence electrons, what we say, because there are so many inner core electrons between the valence electron and the nucleus, we say that the valence electrons on the outside, the outer shell, are, quote, shielded from the nucleus, from that charge of the nucleus, by the inner core electrons. And so the outermost electrons don't feel as much of the attraction to the nucleus as the ones that are closer, the inner core electrons do. And part of that is because they're further away, but part of that is because the inner core electrons have some repulsion. They shield that charge. So we call that shielding. Now if we look at a larger atom, this would be barium, and I know that because it has 56 protons in the nucleus. And I don't know if I drew 56 red dots there. We're not going to count them. We're just going to assume that it's right. There doesn't appear to be right because I see 3 outer shell electrons. That can't be right. But we're just using this as an example. So this Z sub EFF, that's the abbreviation for effective nuclear charge. Z would normally be the atomic number, and that would be the nuclear charge, right? So magnesium's atomic number is 12, which means its nuclear charge, Z, would be plus 12. But its effective nuclear charge, that's basically the charge that the outermost electrons feel. And so we're going to talk about that. So Z is the typical nuclear charge. That would be plus 12 for magnesium, plus 56 for barium. And then S is called a shielding factor. That's basically how much shielding occurs by the inner core electrons. And this is not an equation that we're going to use numerically. I'm not going to give you values and you put in there what it is. This is something we're really just going to talk about qualitatively, not quantitatively. So it's just an idea. It's a concept. Okay, so the idea here is that this outermost electron, this valence electron for barium feels a much lower effective nuclear charge than magnesium's valence electron does. Not only because, number one, it's further from the nucleus, but there are a lot of inner core electrons between this valence electron and that plus 56 nucleus. So even though Z is high, plus 56, there's a ton of electrons in the way. So barium is going to have a lower effective nuclear charge because it has so much shielding going on. So let's use those concepts to talk about atomic radius or size. All right, so here's a periodic table, and this shows that the radius increases as you go down a column, and it decreases as you go across a row or period. We're going to talk about both of these trends one at a time. We're going to start with the going down a column. So size increases as you go down a family or group, which remember is what we call the columns here. Now, why would that be? Why is that true? Now remember, size is defined by the outermost valence electron shell. So if we look at this first group, just the alkali metals, we'll look at this group starting with lithium. Lithium has these 3 electrons. The valence electron, the single valence electron is in the second shell. And then sodium has its single valence electron in the third shell. Potassium, rubidium, cesium. So you can see here that the size of these atoms is increasing because the shell numbers, it's getting more and more electron shells, and the valence electron lives in a shell that's just much further from the nucleus, right? So the atom just gets bigger because it has more electron shells. So if you look here, as N increases, that's the shell number, that's the row number, the size of the outer shell increases, right? So this is in the first shell, second shell, third shell, fourth, fifth, sixth shell. And so that the sixth shell is just much further from the nucleus than the first shell. And so that's a pretty simple reason, I think. I think that makes sense. Now, as we go across, size decreases as you go across a period. Now, this is a little bit harder to understand. Now, so let's talk about why this is. If we look at just this row here, just the boron through fluorine, okay? So boron has a +5 nucleus, carbon is +6, +7, +8, +9 for fluorine. So if we look at these nuclear charges and we draw these out, we're going to start with boron. Boron has a +5 nucleus, and we see these 5 electrons. The 3 valence electrons are in the second shell because this is the second row. Now, if we move forward to carbon, carbon has an extra valence electron, so 4 electrons in the second shell. But it has a +6 nucleus, and so the positive charge in the nucleus is higher than it was before, but it's still only the second shell, and the second shell is the same distance from the nucleus, but because there's a +6 in the nucleus now, it's going to feel a higher effective nuclear charge because Z is higher, right? It's +6 instead of +5. So that higher effective nuclear charge for the valence electrons pull them in a little bit tighter, right? Because it feels more attraction. We move to nitrogen. Nitrogen is +7, and you can see that plus charge is going up. That nucleus, I'm making it look bigger because the positive charge is getting bigger. That's going to pull these electrons in even tighter. And then we move on to oxygen, which is +8. Higher effective nuclear charge than nitrogen, which is going to pull it in even tighter. Finally, the last one is fluorine. Fluorine is +9, which means the valence electrons are going to feel the highest effective nuclear charge for this one. And they're still only in the second shell. It's going to pull them in even tighter. So now if you go back to our periodic table to explain why, what you would say is that as you go across a period, the nuclear charge goes up. So, but we're still only in the second shell. N stays the same. They're all the second shell, which means the distance from the nucleus is the same. Because the higher effective nuclear charge is there, it's going to feel more of an attraction to the nucleus. It's going to pull it in tighter. The electrons get pulled in tighter by the higher effective nuclear charge. Now this is just a picture showing you the atomic radius. It's just a different visual. So the largest atom would be rubidium in the lower left-hand corner. They're actually leaving off this is only 1, 2, 3, 4, 5 rows. There's still another row there, so they're leaving some stuff off. But you get the idea. Lower left-hand corner is the largest. Upper right-hand corner is the smallest, except for hydrogen.